Okay, so let's look at question 3. It's quite a long one, so I hope I can focus this long. Anyway, so we're told to consider a system consisting of 1.5 mole of carbon dioxide at some initial conditions. We're given the schematics of the cylinder, and this is allowed to expand adiabatically. So, adiabatically, so that's an important phrase there. So, let's highlight that against an external pressure, very important point, until the piston has moved outwards of a certain centimeters. Assume carbon dioxide may be considered a perfect gas with a constant volume heat capacity of that. Okay, right. So, what are we then to calculate? Okay, we're asked to calculate those things. Okay, so the first things, it's adiabatic again. So we start with A. What is it? Q is equal to 0 because we have an adiabatic system. But this is against a constant external pressure. So this is actually an irreversible process. So it's Q irr. Not that you have to write that, but this is just for you to start associating these terms with these type of processes, so that you know, because this becomes important later on when we calculate these kinds of properties. And then we need to, I just realized this actually should just be delta S. So again, it's normally delta S total. So my apologies for that little mistake. Oops. So anyway, so that's delta S, so it's delta S total that we're calculating there in E, but anyway, we'll get to that. So back to my point here, so you can write ir or reversible. So when it's reversible, then you write rev, and when it's irreversible, you write ir. Anyway, right, so that's the A part of the question. So then for B, for the work, so how do we calculate the work? Well, we're given the constant, so it's an irreversible process, so then we normally use P external delta V, right? Oh my goodness, P external delta V is what we use to calculate that. So in this case, we're just going to have to think about how we're going to calculate delta V, because we given the cylinder's cross section. So in other words, the area of the cylinder and how much it's moved up. So that's what we're going to use to calculate the volume. And then we're given the pressure. Okay, so we can all plug that all into one step because, we're all really good at mathematics, so that shouldn't be a problem. 1.5 atmosphere. So then the volume is then 100 cubic or 100 centimeters squared times the height of what is moving up, so that's 15 centimeter, not meter, centimeter. Okay, and then this is of course in centimeter. So I just need to think. Anyway, so we'll convert that into liter, which should be in liter anyway. Quite easily. So how much is this? This is 1,500, right? 1,500 cubic centimeter, so that's 1.5 liter. Yeah, that's fine. Okay, so I'll just plug that in, and then 101.3 joule per liter atmosphere. We can use that conversion factor then again to get rid of the atmosphere and get rid of the liter. Okay, so we can use those conversion factors, or we can, if you want to leave that in centimeter, then you can just add another one here that says there is 100 centimeter in a meter, and then that means in a meter cubed in a meter cube there's so much there, and then in 1 liter, I really just need to keep my bearings, and then in 1 liter we want a liter on top, so we want to cancel with, in meters cubed there's 1,000 liters. You can just use those conversions. Anyway, right, plugging that into our calculator, we should obtain minus 227.925, which we then need to round off to 2 significant figures, so then that is minus 230 joule. Right, so that's our work, minus 230 work. So in other words, the work performs, or the gas performs work on the piston. Okay, which actually makes sense because it is expanding. Anyway, C, we're asked to calculate the internal energy. Okay, and we can actually just get this from the first law, so it's not too difficult. So we have an irreversible process, we have some work done. So here the entropy, the internal energy is just equal to our work, so minus 230 joule. Okay, not too difficult. So now in D, we're asked to calculate the change in the temperature. And there's probably a few ways that you can do this, but the way that internal change in temperature is defined, or something that is useful here. So remember, for adiabatic changes, the change in internal energy is defined by the constant volume heat capacity times the change in temperature for 1 mole of gas. So then for not 1 mole of gas, it's defined by the molar heat capacity times the temperature. So in other words, we can get, because we're given all that information, so in other words, we can just rearrange that equation. I do apologize for sort of skipping through the theme 2 things, because it's not my job to teach that. So anyway, so how do we do this? So we just plug it in. So remember, now we're calculating a new quantity, delta T. So we have to plug in delta U's value as in the pre-calculated value, which is actually the W value of the previous one. So we need to plug in this 227.925 value. Okay, over 1.5 mole, that's in joule, and then 28.8 joule per Kelvin per mole. Right, quickly calculate that. Now that is equal to minus 5.276 and some other stuff. And then we need to work to 2 significant figures. No, sorry, 3. That's 1.5 So in other words, we have minus 5.28 Kelvin is our temperature change. All right. Okay. Then, okay, the fun one, number E, so the entropy change. Okay, so now I'll switch into teaching mode. So we need to get the total entropy change. All right, total, and that is of course, as always, equal to the change of the system plus the change in the surroundings. So let's first think for a moment. So it's adiabatic. So when something is adiabatic, we can immediately write something regarding the change in entropy for the surroundings, because the surroundings change is only dependent on the change or the heat of the surroundings. And if it's adiabatic, it means that heat is zero. So in other words, that change must be zero. So whether or not it's reversible or irreversible, the change, so that whether or not what the process is reversible or irreversible, the change in the entropy of the surroundings will always then be zero for an adiabatic process. Right. So that you can take to the bank and you can cash. For the system, it depends. The system depends whether or not it's reversible or irreversible. If it's reversible, then the system's change is also zero. If it's irreversible, it's non-zero. It's larger than zero. Okay. And then it depends on whether or not it's an expansion process or a heating process. And in this case, we actually have both. So how do we treat a process where we have both heating and expansion? Well, so we must think about it in terms of a volume and temperature process. So we have both heating and expansion happening from one point to the other. So we must break it up into two smaller processes, or two iso processes. So in other words, first what we do is we break it up into an isochoric process. So in other words, an isochore, and then we do an isotherm. Right. So that's how we break these processes up for the system. So this is the system's change. Right, we're going to make that clear. So because we have volume changes and temperature changes, and entropy is a state function, right? So we have both changing at the same time. We can actually look at it independently. We can first look at change in temperatures, contribution to the entropy while the volume is constant, and then look at the change in volume's contribution to the entropy of the systems while the temperature is constant. Okay. So we have two equations that help us with that. So the first one, of the total one, is that the entropy of the system is equal to NCVM ln TF over TI. So that is for our isochore. Right, so that's that bottom part. So while the volume is constant. And then we have the next part, which is NR ln VF over VI, which is for the isotherm. So it's while the temperature is constant. Okay. So that's how we sum it. So we sum basically, so the curve is equal to the sum of the two straight lines. That's how we're going to look at that. Right. Now, this involves a lot of little calculation steps, which the first of which is that we require the initial volume, because we only calculated the change in the volume thus far. So we have that the change, well, we actually haven't calculated the change in the volume, I just plugged it in somewhere, which was what? Oh yeah, it was my 1.5 liter. Yeah, so let me just write it down here somewhere. So delta V is equal to 1.5 liter. Just something that I need to remember. Okay. Then VI, I promise this would of course be nicely typed out, so you'll have reference while you're watching this video. So then we can calculate VI from our perfect gas equation. So that would be nRTI over the initial pressure, which is then 1.5 mole. The number of moles don't change. 8.3145 joule per Kelvin per mole times the initial temperature is given as 288.15 Kelvin, and that's all divided by 9 atmosphere, which is the initial pressure. I hope. Yeah, initially at 15 degrees Celsius and 9 atmosphere. That gives us an initial volume of 3.9409,315 liter. Alright. Of course, now we need the final volume as well. Now we can use a nifty little trick, which is that the initial volume, so the final volume is equal to the initial volume plus the change in the volume. So in other words, we have this 3.94 whatever plus 1.5, which is then equal to 5.4409,315 liter. Okay, so now we have everything that we need for this right hand side. We have N, we have R, we have F and VI. Okay, we also have delta T, we have delta I, but we don't have delta F. So let's also use this trick to calculate delta F. So let's do that. So then Ti was 288.15 Kelvin minus, okay, so now we need to use the pre-rounded value again, 276 and some values. Oops, wrong idea. That gives us 282.854 and a bunch of numbers. Okay, so then the entropy change of our system is equal, so now I just need to plug all these values in. As you can hear, I'm having the time of my life. There's nothing worse for me than having to plug numbers into a calculator. I like algebra and things that I don't have to, like, there's nothing more tedious than this, honestly speaking. And then we have the temperatures. So the final temperature is 282.874. Oh yeah, this is Kelvin, of course, my apologies. Over the initial one is 288.15. And this is plus N, which is 1.5 mole. R, which is 8.1345. I always love writing that number because it makes me think about counting. M per mole ln of the final volume. Final volume is 5.44440 and numbers divided by the initial volume, which is 3.94 and some stuff. This is of course Kelvin, and Kelvin is of course liter and liter, Kelvin, liter and liter, and they cancel. And here we're left with, so moles cancel with mole, and we're just left in joule per Kelvin. 3.227 joule. I don't have to write the unit here yet, so we can round this off to how many significant figures? 3. So 3.23 joule per Kelvin. Okay, why 3 significant figures? It's always good just to recap that. There's 3 significant figures, there's 3 significant figures. All the other ones have more than that. Okay. Oops, I'm running out of space, eh? Anyway, you can go there. So delta S total then equal to delta S system plus delta S sur, which is 0, so which is equal to delta S system, which is equal to the 3.23 joule per Kelvin. Right. Great. Huh. That was a long question. Yeah. So, oh my goodness. Let's get back to this again. So, basically, just remember. So, if you have a adiabatic system, what do you immediately know? If so, let's make a little block for ourselves. And let's write in another color. Let's write in blue. So adiabatic has two sides. Adiabatic reversible and adiabatic irreversible, right? Reversible means that delta S system is 0 and delta S sur is 0. Why? This is because Q rev is 0, and this is because, well, Q sur is 0. Delta irreversible system means that delta S system is larger than 0 and delta S sur is still 0. Why? Because Q sur is still 0. Okay, so in both cases it's adiabatic, your surrounding entropy change of your surroundings is 0, but the system one changes. So in other words, for a reversible system, for a reversible adiabatic system, we have that our change in our total entropy is 0. For an irreversible adiabatic system, our change in our total entropy is larger than 0. Okay. So hopefully you've now seen this. So that's question 2 and 3, basically what we've learned from those two. All right. Yeah. And then, of course, you know how to calculate your system. You can break up, for the system, you can break up heating and you can break up expansion according to this equation. So you can break up heating and expansion into two separate what do you call it? Isoplathic systems or isoplathic processes. Right. I hope these videos are somewhat informative and helpful.